Hi everyone. I just received some feedback that the lecture on frequency response was not clear. So I'm just trying to repeat that lecture, and also I'll discuss the impact of the input offset voltages and bias currents in instrumentation amplifiers. Okay, so I'll go a little bit more in detail. I'll explain what I probably discussed in the previous lecture on the frequency response of instrumentation amplifiers. So all I said was, when you are analyzing the frequency response of instrumentation amplifier, the way in which we have to proceed is to split that as a two-stage amplifier. Right? Amplification happens in two stages in instrumentation amplifiers. The first stage is a non-inverting amplifier, but if you look at it, it is actually a differential amplifier, meaning input is differential, output is also differential. So you have the overall instrumentation amplifier can be written like this, can be modeled as a first stage as a differential input differential output amplifier, and the second stage is a differential to single ended converter. So let V1 and V2 and V1 be the input of the first stage, and VO2 and VO1 are the output of the first stage. That forms as the input of the second stage. The output of the final stage is simply given by VO2 minus VO1 times G2. G2 is the gain of the second stage. Okay, let's call this as G2, G1. So all I said was I can model that as a cascade of a fully differential first stage and a differential to single-ended output second stage. That's what I did. I mean, I just said that you can model it, find the transfer function of the first stage, multiply that with the transfer function of the second stage, you get the overall transfer function. So that's all I discussed in the last class. And now when you're finding transfer function, previously we assumed the gains of the amplifiers, the op-amps to be ideal. Therefore G1 was simply equal to 1 plus 2 RF by R, and G2 was simply equal to RF by R3. So the overall gain, G1, G2, so G is the overall gain of the amplifier, was equal to G1 times G2. So let me write my G properly. So this is G1 times G2, and this is given by 1 plus 2 RF by R times R4 by R3. So it's a very straightforward result. Now if I consider the op-amp's frequency response, okay, if I assume that the op-amp's gain is not constant for all frequencies, then how does that impact the performance of your instrumentation amplifier? That's what we want to study here. Okay, look at this. Instrumentation amplifier doesn't have any external capacitors. You don't see any capacitors here. All are resistors. So all the frequency response comes because of the MOSFETs, the op-amps, frequency compensation network and all that. Okay, so generally we said, again, this is something you guys have to keep in mind, is most op-amps, the op-amps that we will analyze in this course, we will assume that the gain of this op-amp, the frequency dependent gain, can be expressed as a DC gain and a single pole. Okay, and we said this holds very true because of frequency compensation. Normally most op-amps employ, at least the IC op-amps employ, what we call as the dominant pole compensation. So usually when you want to realize a high gain, you use a cascade of multiple stages. But multiple stages leads to instabilities. So what do? We make one stage where you get very high gain, or also you make the pole to be at very low frequencies. So for all practical purposes, or for the mathematical analysis, we can treat the op-amp as a single pole amplifier. And this pole occurs at a very low frequency. So if we are interested in finding out the frequency response of these op-amp based circuits, we can usually model at high frequencies, where the gain of the op-amp starts decreasing. At that point, you can usually model the op-amp as an integrator. So this, I've already discussed this, I'm just quickly refreshing your memory. So op-amp's gain can be written as A times omega P by S, right? S by omega P will become much greater than 1. So I can write it as this, which is nothing but omega U by S. For the first stage in this analysis, I'm going to call the first stage, the op amps in the first stage as amplifier A1. So A1 of S is the frequency response of the first stage op amp, can be approximated to omega U1 by S. Okay, this is your frequency response of the op amp. Okay, it's a very useful result. We will use this result throughout this series, okay, towards this lecture series. So now back to the analysis. So all I said was the overall transfer function V0 by Vd of S can be decomposed into a cascade of two transfer functions. The transfer function of the first stage, which is a fully differential amplifier, differential input by differential output, times the transfer function of the second stage, which is a single-ended output divided by the differential input. So, and we will call that as G1 of S and G2 of S. Okay. Now, because that op amp here, these op amps are assumed to have a single pole, the closed loop response will also have only a single pole. That again follows straightforward from basic control theory. Let's say you have a control system with some forward path amplifier with a single pole and a feedback which is independent of frequency. Then the closed loop poles, the closed loop system pole, closed loop system will also contain a single pole. Okay, so that's what I've represented here. I just said that the first stage can be written as a DC gain with a single pole, and here the single pole omega 1 happens to be the 3 dB bandwidth of the first stage, and omega 2 happens to be the 3 dB bandwidth of the second stage, and we will soon find out what is the values of this omega 1 and omega 2. Okay, so now your overall gain of this amplifier G of S is given by G1 of S times G2 of S. Okay, so which will be G1 G2 upon 1 plus S by omega 1 times 1 plus S by omega 2. Okay, so now my goal is to find out what are these omega 1 and omega 2. Then from that knowledge, we will try to draw the overall frequency response of this instrumentation amplifier. So first I'll start with the subtractor or the second stage because it is easier. We have already done the subtractor frequency response, so I'm going to take that. So in any negative feedback system, right, you can actually derive the equation, apply superposition and derive the transfer function for both the stages. Okay, and you can easily show, I'll leave that analysis to you, but you can easily show the transfer function will look something like this. I'll write the DC response. R4 by R3 is supposed to be your DC gain, right, which is nothing but V0 upon V2 minus V1. If you find, you see your output is given by R4 upon R3 times V2 minus V1, right? That's the second stage acts like a subtractor with a finite DC gain, and the DC gain is R4 by R3. In the presence of op amp's gain, if I assume op amp has a finite DC gain, then we can express it as an additional factor given by 1 by 1 plus A beta. Now I'm going to call the second stage amplifier as A3 because there are three amplifiers here, three op amps here. I'll call it A3, so it will be A3 beta. So this result, it's a very useful term. Normally what we do is we take the DC gain of if you analyze any negative feedback amplifiers, op amp based amplifiers, this result holds true generally. Okay, what do I mean by this result is that you take the DC gain of the circuit, let that be some DC gain G, and you can, if it's built using single op amp, the circuit is built using a single op amp, you can then model that op amp, the op amp circuit, as some DC gain A0 times 1 by 1 plus A beta, A beta, right? A beta is op amp's DC gain, and beta here is the feedback network, is the feedback factor for that op amp circuit. So again, this is, guys, I'm just telling you this, that how to, it's a useful result to remember. That's why I'm talking about this. If you want, I'll just quickly tell you guys what it means. So if you take any negative feedback system with a forward path gain A and a feedback path gain beta, then the overall gain is given by A by 1 plus A beta. This can be written as 1 by beta times 1 by 1 plus 1 by A beta. So this is what I meant. Here 1 by beta is the DC gain, is the nominal gain of this amplifier. That can be then has to be multiplied with 1 by 1 plus 1 by loop gain. This term A into beta is called loop gain. So generally for most feedback amplifiers, op-amp based in feedback amplifiers which use op-amps, you can express gain in this format. And it will come very handy when we are doing frequency response analysis. So that's why I'm writing it in that format. So let's come back to this result. So I'll start with this result. So the gain can be expressed as R4 by R3 times 1 by 1 plus A beta. This A3 of S times beta is the loop gain of this op-amp circuit. So you can apply the standard procedures for finding loop gains, but this circuit, since we have already analyzed it, I'm going to directly write beta in this circuit is given by R3 by R3 plus R4, which can be written as 1 by 1 plus G2. G2 here is R4 by R3. And A3 of S can be approximated to omega U3 by S, right? This is again a op-amp with a single dominant pole. So we can express that the transfer function or the frequency response of this op-amp as omega U3, the UGB of the op-amp upon S. So substitute these two results here, you will get this expression. G2 times 1 by 1 plus S into 1 plus G2 by omega U3. So all it says here is that the subtractor acts like a single pole low pass filter with a finite DC gain. And that low pass filter's 3 dB bandwidth, omega 3 dB, is given by omega U3 times beta. So in the previous lecture, I just directly quoted this result. I didn't derive it. I just directly quoted it because I already derived it in the subtractor lecture, which is why I directly quoted it. So that's what I've written here. And since beta equals 1 by G2, here omega U3, the UGB, the 3 dB bandwidth of the second stage is given by omega U3 by 1 plus G2. Okay, the DC gain of this second stage is G2 and this. So this here is simply V0 of S upon V2 of S, VO2 of S minus VO1 of S. That's the second stage transfer function. Now deriving the I'm sorry, just let me so now sorry for that. So now deriving the frequency response of the first stage is much simpler because it's a fully differential amplifier, right? You apply a differential input and the output is also differential. Since it's a fully differential amplifier, we can use the concept of half circuit. I can just analyze a half circuit and use that as the overall transfer function. The half circuit reduces to this, right? In the R you can write it as R by 2 and the half circuit for this circuit is given by this. How do you draw half circuit? I've already explained it before. So this resistor can be written as R by 2 and series with R by 2. This node will be a differential AC ground. So I can just analyze one half of the circuit and find the transfer function. Thus, the transfer function of the one half, the differential half circuit, can be treated as the transfer function of the overall differential amplifier. Now this becomes a non-inverting amplifier. Again, for a non-inverting amplifier, the overall gain, remember this result, can be written as 1 by beta times 1 by 1 plus 1 by A beta. Okay, the nominal gain, which ideally it's supposed to be, if let's assume A is infinity, it's supposed to be just 1 by beta. But here, because op-amp's gain is finite, the loop gain will also be finite. Therefore, the expression becomes 1 by beta times 1 by 1 plus 1 by A beta. And this A beta is your loop gain, LFS. In this case, I'm going to use this terminology. We called beta 1 as the feedback factor in the first stage. So beta 1 is the feedback factor in the first stage. So I'll write it as 1 by beta 1 times 1 1 by 1 plus 1 by A1 of S times beta 1, where A1 of S is the frequency response of the first stage op amp, the op amp in the fully differential amplifier. So I'll again use 1 by beta 1 is simply G1. G1 is the gain of the first stage. Beta 1 is simply the feedback factor, R by 2 upon R by 2 plus RF. Take R by 2 to the denominator, you will get G1. I mean, you will get 1 plus 2 RF by R1 R into 1 by that, which will be just 1 by G1. So now the gain of the first stage can be expressed as G1 times 1 by this expression. I have written this 1 by 1 plus 1 by A1 of S times beta 1. A1 of S, I can replace it by omega U1 by S. So it becomes omega U1 and S goes to the numerator. So now you get a single pole response like this. Since beta 1 is 1 by G1, the pole frequency of the first stage pole frequency, which we will call omega 1, is given by omega U1 by G1. The frequency response of the first stage will look something like this. Okay, DC gain is G1 and the 3 dB bandwidth, the first pole occurs at omega U1 by G1. Okay, I just used this result to derive it. You can just do a quick KCL and KVL, but by now, you should be able to, because we have discussed so many op-amp based circuits, you should be at a position where you're comfortable enough to derive these results yourself. Okay, so now that we have the gain expressions for both the stages, now to find the overall gain, I just have to multiply the transfer functions of the two stages. Now you are left with two poles. How will the frequency response of a two-pole system will look like? The gain will start drooping at the rate of minus 20 decibels per decade when it encounters the first pole. When it encounters the second pole, the gain will start drooping at the rate of minus 20 decibels per decade, minus 40 decibels per decade. Okay, so if you take a single pole system, the 3 dB bandwidth of the single pole system is equal to the pole itself. But now when you have two poles, the second pole will also contribute to some amplitude attenuation near omega 1. So the 3 dB point is the point where your gain becomes G1 G2 by root 2. The magnitude of the gain becomes G1 G2 by root 2. That will occur slightly before U1, because omega 2, see that omega 2 will also start impacting the gain. So what's your gain magnitude? G1 G2 upon root of 1 plus omega by omega 1 the whole square. This term multiplied by 1 plus omega by omega 2 the whole square. So there are two terms, okay, which decrease with frequency. So the omega 2, the second pole, will slightly attenuate the transfer function. So therefore the frequency at which the magnitude becomes 1 by root 2 of its DC value will be slightly lower than omega 1. You can easily see this. Let's assume omega 2 is infinity. If omega 2 is infinity, then it will look like a single pole system. Then the 3 dB bandwidth will simply be equal to omega 1 itself. Or if omega 1 is infinity, let's assume omega 1 is so high that I can treat it to be, that I can ignore it, then the 3 dB bandwidth of this differential instrumentation amplifier is omega 2. So that's why I wrote this expression. In general, the 3 dB bandwidth of a instrumentation amplifier will be lower than omega 1 and omega 2, the 3 dB bandwidths of the two stages. And we saw how to derive the expressions for the two stages. Omega 1 is given by omega U1 upon G1, and omega 2 is given by omega U2 upon omega U3 upon 1 plus G2, the second stage gain. And we said in general, whenever we are programming the gain, we normally program the first stage gain. Okay, in general, G1 will normally be much greater than G2. So therefore, the first stage op-amp, especially when you're designing it for very high gains, right? Whenever your G value is in the order of thousands, then you know automatically G1 is really high. That's why you have designed it You have set G1 to very high values. I showed you some examples from data sheets. I showed you two instrumentation amplifiers, wherein in the first instrumentation amplifier, all the gain, the entire gain of the amplifier was entirely due to the first stage. Second stage gain was just unity. It was just acting like a unity gain, just a subtractor or a simple differential to single-ended converter with a unity gain. So since most of the gain comes from the first stage op-amp will dictate the frequency response of the overall instrumentation amplifier. That will dominate. So as a circuit designer, if let's say you are an IC designer who's designing the instrumentation amplifier, then you have to ensure the first stage's UGB is really good, especially for high gain settings. Okay, generally, what does high gain mean? High gain means the feedback factor becomes very small. If the feedback factor becomes very small, then the 3 dB bandwidth also becomes smaller for these amplifiers. That's all this means. Okay, that's what I said. As far as a circuit designer is concerned, who's going to design a differential instrumentation amplifier, he has to take care of the first stage amplifier very well. Okay, that's what is going to contribute to the speed. Okay, so that has to have a high UGB, especially if you want to have a high gain. So that's the conclusion. Okay, so whenever you have any two-stage systems, when you cascade two single pole systems, the lowest of the two poles will always dictate the overall response of the system. So that's all I was trying to say, and I gave you an example. Assume omega 2 is infinity. If the omega 2 is at very high frequencies, then the 3 dB bandwidth of the system will be equal to omega 1 itself. Right? The lowest of the two determines the overall response. I mean, this is something looking at it from frequency domain, but you can also look at it in time domain. You can just quickly analyze, you can perform a very quick step response for this two pole amplifier. If you do that, I'll leave that analysis to you guys. You can easily show that the step response will contain two exponential terms. One exponential term will be due to the first pole, another one due to the second pole. And if you looked at these expressions, right, the first pole will be multiplied by a much higher factor compared to the second pole. Okay, when I say first pole, I'm usually calling it as the low frequency pole. Omega 1 here is less than omega 2. That's the low frequency pole. So the low frequency pole will be multiplied by a term which will be much higher than the scaling factor with which you will multiply the second term. So that's all I'm trying to say here. Okay, so if you plot this overall response, right, there are two responses. There is a response due to the first pole, response due to the second pole. All I'm saying is the response due to this first pole will be the dominating factor. It will almost look like a first single pole response with a time constant given by 1 by omega 1. Here I'm assuming omega 1 is much less than omega 2. Okay, you can plug omega in this equation. As I said, I'll leave this as an exercise. I think I have not fully discussed second order systems in my passive devices lecture series. Maybe someday I'll get a time, I'll make some video, or probably in this course itself, when I start talking about second order systems, I'll talk in greater detail there. It will look very intuitive for you guys at that point, but you can see here itself, in this mathematical expression itself, that the first pole is multiplied by a term which is much greater than what it is multiplied for what the second pole term is getting multiplied by. What does this mean? It simply means that if I just let's do this, let me take this term omega 2 upon omega 2 minus omega 1 common out, then I'll be left with this 1 minus this minus omega 1 upon omega 2 times e power minus omega 2t. See, right, this term will be much smaller than 1 if omega 1 is much smaller than omega 2. So the exponential due to the second pole is almost negligible. So you can ignore it. You can treat it like a single pole system which is going to decay with a time constant, or it's going to exponentially rise with a time constant 1 by omega 1. That's all I meant. Okay, so if you have a cascade of two stages, the lowest pole will dictate the overall bandwidth of the system, or in time domain, I can explain it as the time constant of this overall cascaded system will depend upon the time constant of the slower system, or the time constant corresponding to the lowest pole. Okay, that will have a larger time constants. So tau 1 will obviously be much greater than tau 2 because omega 1 is much less than omega 2. So the larger of the two time constants will dictate the overall time constant. So this is explaining in time domain point of view. So that's it, guys. So just keep in mind, see, when we are doing this analysis, frequency response analysis of the instrumentation amplifier, I want you to be comfortable with the analysis that I've carried in this lecture. The main reason being that for circuit designer, see, when I'm teaching analog electronics, I'm teaching it because I'm an IC designer. I'm teaching it from an analog IC design point of view. Okay, as well, I'm also giving some basics about components and all that, but mainly I'm teaching it from an analog designer's point of view. So if you are just preparing for an entrance exam, it's okay, you can skip some parts of this if you don't fully follow. But if you are planning to be an analog engineer or a mixed signal design engineer, you have to be comfortable with all of this. Okay, so that's why I recommend you go through this. So that's it about the frequency response. I'll now, in the next lecture, we'll talk about the impact of offsets.